So far in quantum mechanics, we've mostly thought of particles as independent entities. We presume that the state we see for one particle does not depend on the state we see for another. In the classical world, this seems so obvious that it's hardly necessary to state it. Of course, the state of some object is just a property of that object, and the state of another object is similarly just a property of that object. But in quantum mechanics, this separate reality for objects does not necessarily hold. Different quantum mechanical systems can be linked with each other in a way that has no classical analog. This makes their joint state intertwined, or as we say, entangled. Strange as these ideas may seem, we can actually see them in the laboratory in carefully constructed experiments. The fact of entanglement is not in doubt experimentally. Here we're going to look at this concept of entanglement, and we'll start to examine some of its quite bizarre consequences.
We need to re-examine the states of more than one particle. Suppose we have two particles. For example, that could be two photons. So here they are. And we could presume that photon 1 is in one of a set of possible states, psi m, so those are the possibilities, different values of m perhaps, and the 1 here means we're talking about photon 1. So here's our state of photon 1. And we'll presume it's going to the left, as shown here, for example, and it's in some particular spatial mode, that is, a particular beam shape. And also, it'll have some specific frequency. And the different possible states of this photon would then be vertical, for the polarization state, or horizontal. Photon 2, similarly, is in one of a set of possible states, and we call those phi and n for the possibilities here, and the 2 for the second photon. So here's the second photon state. And we presume, for example, it's going to the right in a particular spatial mode or beam shape with a specific frequency and with the different possible states being vertical or horizontal polarization. Then, appropriate basis states for the left-going photon 1 would be horizontal 1 and vertical 1. And similarly, appropriate basis states for the right-going photon 2 would be horizontal 2 and vertical 2. Now, a possible state of these two photons is this one here, which corresponds to the left-going photon, that was number 1, being horizontally polarized, that's the H, and the right-going photon, that was number 2, being vertically polarized. Other examples with obvious meanings include states like the following: both photons horizontally polarized, both vertically polarized, and photon 1 being vertical and photon 2 being horizontal, the opposite way around from the state we talked about up there. We can express other polarizations of a given photon as linear combinations of horizontal and vertical. For example, this state here describes a left-going photon, that's photon 1, polarized at an angle of 45 degrees. Hence, a state like this corresponds to the left-going photon, number 1, polarized at 45 degrees, and the right-going photon horizontally polarized. So photon number 2 is horizontally polarized. So far, we've assigned each photon a definite polarization, just as we could classically. But these states are not the only ones allowed by quantum mechanics. For example, consider the following state of the two photons. So this one here is a possible state. It's a linear combination of these basis states. So that's a linear superposition of the state where both photons are horizontally polarized and the state where both photons are vertically polarized.
It's relatively straightforward with modern techniques to generate pairs of photons in states of this general type. One approach is what is called spontaneous optical parametric downconversion, which is a second-order nonlinear optical technique. A pair of photons in a state like this is sometimes called an EPR pair, after Einstein, Podolsky, and Rosen. And the state itself is sometimes called a Bell state, after John Bell.
A state like this one is a linear superposition of two of the states we considered already. Quantum mechanically, it's quite a valid state of the system. It's a vector in the four-dimensional Hilbert space that describes the polarization state of two photons. That's a direct product space in which all of these functions here are appropriate orthonormal basis vectors. The state that we've written here, though, is very non-classical. It cannot be factorized into a product of a state of particle 1 and a state of particle 2. States that cannot be factorized into a product of the states of the individual systems on their own are said to be entangled. In such an entangled state, particle 1 does not have a definite state of its own, independent of the state of particle 2. Imagine we measure the polarization of the left-going photon, photon 1, and find its horizontal. Then we have collapsed the overall state into one that now only has terms in photon 1 being horizontally polarized. So the state of the whole system is now this one.
By measuring the state of the left-going photon and finding it to be horizontal, we've also collapsed the state of the second, that is the right-going photon, into a horizontal polarization, even though we did not sort of touch that one. The state of the right-going photon depends on the state we measure for the left-going photon. And this is true even though both results are possible for the measurement of the left-going photon. In our classical view of the world, this really does not make sense. It defies our normal understanding of states and even of causality. In this strange world of entangled states, it's by no means clear that measuring one particle causes the collapse of the other. It's not apparently possible to use this to communicate faster than light. Looked at separately, both of these measurements are apparently random processes. All we know is that these measurements always give the same result for the measured polarizations, horizontal or vertical, of both photons.
There are three other states like the one we already considered. So here's the one we've written so far, and here's another one, and here's yet another one, and here's a fourth one. And these together constitute what are called the four Bell states after John Bell. And these four Bell states are orthogonal to one another, which you could check, and they form a complete basis, therefore, for describing any such two-particle system, with two basis states per particle, here horizontal and vertical.
There are many bizarre and important consequences of entanglement for the meaning of quantum mechanics. Here we want to emphasize that, once we consider the states of more than one quantum system at a time, there is a whole additional range of states in quantum mechanics, these entangled states, that have no analogue in the classical view of the world.
For the two particles considered here, each with two basis states, the required Hilbert space, as we've seen, is four-dimensional. So the most general quantum mechanical state of these two photons is one like this, where now we need four generally complex coefficients. And those are the four different C's in this formula here. So this is a set of orthogonal basis functions, if you like. The Bell states were as well. But this one will do to describe any possible polarization state of these two photons. But note, it needs four complex coefficients here to specify the state of just two photons.
Classically, just one complex number is enough to specify the relative amplitude and phase of the two polarization components of one photon. We would need at most two complex numbers to specify the polarization state of two photons in this classical view. But note that we're saying here that quantum mechanically we need four complex numbers, not two, to specify the polarization state of just two photons. We need four because we may have to give a different amplitude to each of four different orthogonal basis states. We need four basis states for the full quantum mechanical description of the polarization state of two photons. The situation becomes even worse as we increase the number of particles. Even restricting to particles with only two basis states of interest, the dimensionality of the direct product Hilbert space, and hence the number of expansion coefficients we need to specify the state, rises very quickly.
For 3 particles, for example, we need 8 coefficients. For 4 particles, we need 16 coefficients, and so on, leading to 2 to the power n coefficients for n particles. 300 particles, therefore, would require 2 to the power 300 coefficients, and that number may actually be larger than the number of atoms in the observable universe.